All right, welcome to lesson 4.3. In this lesson, we're going to be sketching with vertical and horizontal asymptotes. And this is another long lesson for us. Now, this lesson touches on things that we already know how to do from other prior courses, especially advanced functions. We know how to find vertical asymptotes and we know how to find horizontal ones. But specifically on this test, I'm going to be looking for the calculus techniques behind this work. You can still be using the advanced functions ideas, though, to help you check your work. All right, so we're going to start off with a notation, side note. Infinity is not technically a number. So when I do the limit, let's see here, I've got 1 over x minus c, and hopefully you recognize that as the reciprocal function from grade 11. It's just been shifted over c units. Now if I approach the c value from the right, or approach the c value from the left, the limits are not going to exist because as I get closer to the vertical asymptote, so hopefully you remember this function, let's say the c value is here, I've got then a vertical asymptote and my function would be approaching from the right, it would be approaching positive infinity, and from the left it would be approaching negative infinity. So I say that the limit from the right is positive infinity, even though this is technically not a limit, because a limiting number would have to be like a maximum amount or a minimum amount. But so we just write this for convenience, and you'll see this all the time in mathematics that people use this as a shorthand. All right, so vertical asymptotes and limits. The graph of f at x has a vertical asymptote at x equals c, if any one of the following things are true. So if I approach from the left and the limit is approaching positive infinity, or if I approach from the left and the limit is negative infinity. And I don't care what's happening on the right side in either of these cases. If one of these things is true, I have a vertical asymptote. And vice versa, if I approach from the right-hand side, so from the positive side of c, and I either approach positive infinity or negative infinity, then I have a vertical asymptote. And again, I don't care in this case what's happening on the left-hand side. Maybe it's also approaching like negative infinity, or here maybe it's also approaching negative infinity. Maybe they're going the same way. Maybe the function doesn't exist over here at all. I don't really care. All I'm asking about here is there a vertical asymptote? And yes, there is, as long as it's infinity on one side. All right. The next part is horizontal asymptotes and limits. So we need to remember that horizontal asymptotes are related to end behavior. So I am talking about what's happening at the end of the function as x approaches positive or negative infinity, and that's how we wrote it in advanced functions. As x approaches positive infinity, comma, y approaches what? And then same thing for the negative infinity. What's really hard for people to get their mind around is since horizontal asymptotes are only related to the ends, when x is this huge number on the left or huge number on the right, it's actually okay for the graph to cross a horizontal asymptote if it's in the middle. So we're going to see an example like that in our work today. So let's say I've got my horizontal asymptote and I've got my function approaching it on the right and approaching it on the left. It's okay if it comes through here and maybe there's like also a vertical asymptote here. This is okay that it crosses it because this is going to be near what we're going to call the middle of the graph. Even x equals 1,000 is technically kind of in the middle when you imagine going to positive 1,000,000,000,000 or even further. So it is okay to cross a horizontal asymptote. A horizontal asymptote only refers to the behavior at the ends. I don't care what's happening in the middle. It's possible for to have a horizontal asymptote on one side of the graph, but not on another. So perhaps, so here I've drawn the horizontal asymptote and it's approaching on both sides, but perhaps on this side it actually goes way up to positive infinity and ignores this horizontal asymptote, and that's okay as well. It's still a horizontal asymptote on the left. Okay, so I do want to remember this trick from advanced functions because it's going to help me check my work only. So this is just to check. I'm not going to write anything of this down on my test as like a justification. But remembering that if I have a rational function, p of x over q at x, then I can figure out if there's a horizontal or oblique asymptote. If the degree of the top is less than the degree of the bottom, so maybe I have a linear over a quadratic, then the horizontal asymptote is y equals 0. So if it's less, the degree of the top is less than the degree of the bottom, I get y equals 0. If the degrees are equal to each other, then I find the horizontal asymptote by dividing the leading coefficients in front of those terms with the largest exponent. And then finally, if the degree of the top is bigger than the degree of the bottom, then I do not have a horizontal asymptote, but I might have an oblique. The oblique asymptote is going to happen if the degree of the top is exactly one more than the degree of the bottom. So if I had like a quadratic over a linear, or a cubic over a quadratic, they're one apart. And so if I had something like this, or something like this, then I'm then I'm going to have an oblique. If you had something like this, there's no oblique or horizontal. Whereas both of these examples had no horizontal, but they did have an oblique because there's only one difference in the exponents. All right, so now we're going to talk about what's the calculus method. Now that I know that shortcut to kind of check my work, what's the actual math behind that shortcut? We're going to investigate the end behaviors by looking at the limit of the function as x approaches positive infinity and the limit of the function as x approaches negative infinity. So this kind of reminds us of writing end behavior in advanced functions. We would write as x approaches positive infinity, what does y approach? And now we use limit notation. This is a more sophisticated way to do it. Now, if I get either the limit on as x approaches positive infinity equals L, so this is just some number, or the limit on the left is equal to L, then y equals L is my horizontal asymptote. And they might both equal the same, or like we said before, sometimes one side will go like to an infinity and the other side will approach a certain value. All right, so to evaluate the limits of rational functions at infinity, what we do is we factor out the highest power of x in the numerator and the denominator. So this is our trick, how to evaluate limits at infinity. All right, so let's give it a try here. We are going to look at part A. I'm finding the limit as x approaches infinity of this function here. So this one's actually a little bit simpler. I'm not going to use my trick yet because I already have a very simplified function here. I'm going to remember my properties of limits from chapter 1. And they tell me that I can, so this is equal to the line above, so I'll start with an equal sign. It tells me that I can separate the limit across subtraction. And so I'm just going to take the limit of the first part of the equation and subtract the limit of the second part of the equation. Now, I think the second piece here is the easiest. As x approaches infinity, 3 is still 3. Because there's no x involved here. So you might remember that from chapter 1. When I take the limit of just a number, it's just the number. Now this one here, I'm going to imagine x as this giant, giant number, and it's like I have $1 up here and I'm splitting it between this giant number of people. So if I do 1 divided by 1,000,000,000,000, I'm pretty much getting nothing there. So this is about 0, and then I can simplify this as -3. All right, now we're going to try B. Now B is a little bit trickier because I don't have a subtraction or an addition, and there's multiple x's, so I've got x's in the numerator and denominator. So I'm going to try this trick here of factoring out the highest power of x in the numerator and the denominator. So I still haven't taken the limit, so I continue to write it down until I actually sub in infinity, and I'm using that term like sub in infinity kind of loosely. The numerator is already factored. It's already written as a multiplication statement. I'm going to take this denominator, and the highest power of x is x to the power of 1. So that's what I'm going to factor out. So I'm going to divide this first term x by x, and I get 1. And then the second term is -6, and if I divide that by x, I get 6 over x. And now what happens is I have a common factor of x in the numerator and the denominator. So now I can cancel. Remember, it has to be factored before you can cancel. So now I have the limit of this expression. And this is what you want when you're taking the limit as x approaches infinity. You want the x to be in a denominator, because as soon as I have that, if I'm taking, as soon as I have taking the limit, and this can be positive or negative infinity, it doesn't matter. If you have some number over x here, so k is just some number up here, then it's going to be equal to 0 when I plug in infinity. I don't care how many dollars you have. If you split it between a gazillion trillion people, you all pretty much have $0. So this is the expression that we're looking for. So as I take the limit as x approaches negative infinity, 2 is still just 2, 1 is still just 1, but negative 6 over x will turn into about 0. And you can say subtract 0 or add 0 here. It doesn't really matter because it's 0. All I'm left with here is 2 over 1, and so I have 2. All right, in C, we're going to use the same trick here because I have a fraction with x's in the numerator and the denominator. So when I look at the numerator, the highest degree on x is 1, so I'm going to factor out an x to the power of 1. So I'm dividing x by x, I get 1, and dividing negative 7 by x, I get negative 7 over x. And remember, this is what we want, are these like little fractions with x's in the denominator. In the denominator here, the biggest exponent on x is x squared, so that's what I'll factor out. When I divide the first term by x squared, I get 1. When I divide the second term by x squared, 3x divided by x squared gives me 3 over x. Right? So I had 1x in the numerator and 2 in the denominator. 1 cancels and I'm left with 3 over x. And then the last term is negative 2, and I'm going to divide that by x squared. Not quite ready to take the limit yet. I'm going to cancel out. I've got an x over an x here. So what this gives me is 1 over x, and then there's also these brackets involved. And since it's multiplication between these brackets, I can actually separate these two fractions and imagine them as two fractions with a multiplication sign in between them. And that works because the entire numerator is, I'm separating a multiplication, and in the denominator I'm also separating a multiplication. And remembering my limit properties from Unit 1, I know that I can then take the limit of the first expression and multiply it by the limit of the second expression. All right, so now I'm taking the limit of 1 over x, sorry, this is an infinity, as x approaches infinity, and that's going to be 0, right? I know when I plug in a large number in the denominator, I get 0. And then over here, when I plug in the infinity, I'm going to get 1 is still just 1. 7 over x is going to go to 0. And in the denominator, 1 is still 1. 3 over x will go to 0. And this is negative 2 divided by that huge number squared, so even bigger number. So I'm also going to get 0 there. And again, I'm not going to be fussy about your plus minus signs. You could actually reason through, and some of the zeros will be on the slight negative side and some will be on the slight positive side, but I'm not going to worry about that this year. So anyways, what I have here is 0 times 1, which is just 0. All right, so this was just practice with some limits. Now we're going to apply them to some actual questions. Oh, sorry, I forgot about this part. First we're going to talk about oblique asymptotes, and then we'll apply all of our knowledge to some questions. So finding the oblique asymptotes, you may have covered this in advanced functions. I know it's one of the things that I removed this year. This is a division line. If f at x equals p over q, then the equation of the oblique asymptote, we can find it just by dividing the p by the q. So I'm just taking the p, and it's the thing I'm dividing. I'm dividing by the q, the denominator, and then the divisor, or the answer, is going to be my oblique asymptote. You can use synthetic, or you can use long division for this. Either way, whichever division I'm using, since the remainder is going to go to 0 as the x value approaches infinity, then I can ignore the remainder. So I don't even care if there's a remainder at the bottom of my division, it just goes away. And I'll write that out as a statement for this example so that kind of makes more sense. So we're going to find the oblique asymptote here. Of this one, I'm going to use long division. Again, synthetic is fine. If you don't remember it and you prefer it, then you should find a video online reminding you how to do that. So with long division, I look at the first term and the first term, and I'm asking myself, what do I need to multiply x by to get x squared? And it's x. I stack that above the x column. And now we do x times x is x squared, and x times negative 2, so I'm just multiplying it through the divisor. And then I subtract. The first term should always go to 0, and then subtracting here, I'm actually going to add the 2x, and I get x. Then I bring down the negative 6. And now I play the same game. This time I'm looking at the first term in the divisor and the first term where I've left off here. So x times what will give me x? Positive 1. And then I multiply that through the divisor. And then I subtract. So here I'm going to get negative 6, and again I'm subtracting negative 2, so adding 2, and I get negative 4 as my remainder. So therefore, the oblique asymptote is just y equals the quotient. And just to explain the whole remainder bit, remember from advanced functions that when you wrote your statement, you would say that the original function here is equal to, sorry, like this division statement here is equal to the quotient plus, minus the remainder divided by the divisor. You might remember this from advanced functions, but because x is approaching, I'm thinking about on the edges of the graph here, as x goes to infinity, then this is going to be infinity minus 2 in the denominator, which is still super big, and so 4 divided by that almost infinity is also going to go to 0. And so that's why I can just ignore the remainder. It doesn't actually matter. I'm going to end up with just x plus 1. Normally you wouldn't write this part down here about justifying the remainder. I'm just trying to explain it for this particular example. All right, so far when we sketch our curves, we're going to go through these steps, and you've already been working with steps 2, 3, and 4. We're just adding on step 1 here. The order doesn't matter. You do not have to complete the steps in order, and you may not have to do all of the steps for all of the questions. So for instance, if you're looking at like a cubic function, don't worry about asymptotes because you know that cubic functions don't have them. Okay, so for asymptotes, what we're going to do is check for domain restrictions, discontinuities, vertical asymptotes, and holes. If there's some vertical asymptotes, I'm going to evaluate the behavior near those vertical asymptotes. So this is my left and right-sided limits. And then for horizontal asymptotes, I'm going to be using the limit as x approaches infinity. And then oblique asymptotes, I'm using the division. And then you know how to find x and y intercepts. Sometimes we're going to have to look for other nice points, and you're going to see that in some of our examples today. When I have like kind of a gap in my graph where I don't know anything about it, I'll just pick some x values and find the y's. And then we talked about minimum and maximums and intervals of increase and decrease the other day. All right. Alright, before I get started on example 2, I'm just going to pause the video and we'll restart again.